everyone. It looks like the room is full, but I hope that there will be more seats available, either up or elsewhere. We just heard an ITC colloquium by Katie Alatalo, and she will also speak at the lunch. We will start with our own Charlie Conroy, who will talk about semi-resolved stellar populations in space and time. And then we'll continue with Andy Szentgyorgyi, also from the CFA, that will give the CFA colloquium later today about the GMT and its significance for future science. But at lunch, he will tell us about the specific application, why you need the world's largest telescope to find Earth 2.0. And then we'll hear from a visitor spending a sabbatical here from Barcelona, Licia Verde. She's a Radcliffe Fellow and spending the year here. And she will talk about neutrino mass limits, robust information from the power spectrum of Galaxy surveys. And finally, we'll hear from Katie Alatalo about, from the Carnegie Institute, about the origins and properties of molecular gas in early type galaxies. I should mention this is the one before last luncheon of the semester. So the next week we will have the last luncheon before the holidays. Charlie.
Great, okay. I want to spend just a few minutes talking to you about this interesting regime of semi-resolved stellar populations. So the idea here is, we're used to thinking about things in fully resolved space, like taking images of star clusters and measuring photometry for all the stars in the cluster and obtaining color magnitude diagrams. And then just more distant galaxies, where you might think of the galaxy as basically a few pixels, and all the light is sort of just in a couple pixels. There's a lot of parameter space in which you actually have galaxies spread out across a detector, such that you have interesting sort of new phenomenon emerging. So to sort of orient things, again, with resolved stellar populations, like this is an image of a globular cluster with HST, you can really resolve every star in the cluster. And one way of thinking about this is in terms of a parameter, the average number of stars per pixel or per resolution element, which in this regime is much less than 1. So that you've got all the light from stars sort of well separated. In contrast, in the semi-resolved regime, this parameter can grow fairly large. And so what I'm showing here is a simulation where the mean number of stars per pixel is 0.1. And I'll increase just to give you a sense of how this goes. So 1, 10. When you get to about 100, you're in the regime where if you imaged the bulge of M31, you'd be in this regime with HST. Even our nearest L-star companion is already in this very crowded regime. 1,000, 10 to the 4, 10 to the 5. Now you're in the regime of galaxies in the Virgo cluster imaged with Hubble. And this is, there's this modeled appearance. There's a lot of information here. This is the regime of surface brightness fluctuations, for those who are familiar with that idea. It's used as a distance indicator. And the idea, a key point is that although the number of stars per pixel is large, the number of those very most luminous stars, the evolved asymptotic giant branch stars and so on, is quite small per pixel. And so you still are in the Poisson-dominated regime for those bright stars dominating the light, which is why you still see this modeled structure. And so the idea is there's a lot of information here still in the stellar population, and we're analyzing these type of data now. I want to talk about one particular application, which is stellar populations in the time domain. So you've seen this nice sort of image to highlight the zoo of variability of stars, from solar-like to Miras to white dwarfs, et cetera, et cetera. We're going to focus on the Miras. These are very luminous, 10,000 solar luminosities, very cool, just a few thousand Kelvin. They're evolved asymptotic giant branch stars, so the last few million years in the life of a star like the Sun. They're also known as long period variables. This is a light curve of the archetype Mira over 40 years. The periods are longer than 200 days. They can be as long as 1,000 days. And the amplitudes of the variation can be substantial, order larger than a magnitude. It's believed that they're pulsating predominantly in their fundamental mode, which means that the period tells you something about the mass and the radius, and therefore the age. So the periods tell you something about the age of the population. So it's a useful diagnostic. And the question I want to get into here is what effect, if any, do these stars have on the light from nearby galaxies in this semi-resolved regime. To address this question, we developed a new set of time variable stellar population models. When people normally make models for galaxies or stellar populations, they ignore any time variability. So we've added that in as a new ingredient into these types of models. In particular, we took data from Ogle. This is for the bulge of the Milky Way, the plot of amplitude versus period. These are the miras. We defined a few sequences here, just empirical sequences. We then took standard stellar evolution models, and these stars up here in the upper part of the asymptotic giant branch, we assigned periods based on assuming they're pulsating in the fundamental mode. And that's basically the model. It's pretty simple. So we just added onto the standard models a period and an amplitude from the data. What we then did was made a model for time variability for the nearby giant elliptical galaxy M87, and you'll see why we chose that galaxy in a moment. This is a movie. So the movie spans 1,000 days. Obviously sped up. This is the model, sort of the actual brightness, and this is the model where we divided by the mean flux at each pixel, mean over the baseline. So you can see, if you look carefully, you see the fluctuations in time. So you're seeing two things. At a given time, the fluctuation from pixel to pixel is due to the surface brightness fluctuation effect, so the Poisson variation in the giant branch. And then at each pixel, you're seeing the contribution from 1 to 3 to 5 to 7 Mira stars adding together. So the average number of Miras, or LPVs, per pixel here is a few. The scale here, in terms of the image, is about plus or minus 0.5%. So it's a subtle effect. We then asked, what is the best data set in the HST archive to look into this? And it turned out M87 had been observed over 72 days for a microlensing campaign. And this was the best data that we found in the archive for this. So what we did was we constructed pixel light curves based on the data. So we sort of partly re-reduced the data in order to ensure that it's super stable and there's sort of free of systematics. And what's shown here is a gallery of some of the more interesting pixel light curves that you see in the data. So you see linearly rising and falling curves and semi-periodic curves, all kinds of interesting things. And again, notice the scale is very subtle, right? It's 0.5% or so. We then observe the model in the same way. That's what's shown here. These are the underlying model light curves, and then the points are sampling the model with the same cadence and Poisson uncertainty as the data. And again, you see the similar kinds of behavior of things rising, things falling, sort of. Because you've got multiple variables adding with random phases, you can get sort of odd-looking features and so on and so forth. And obviously, the ideal observing baseline would not be 70 days, but would be at least a whole period, so several, maybe 300 days or so would be an ideal observing window for this. You can then sort of come up with a couple ideas for how to quantify this variation to at least provide some quantitative tests between the model and the data. We did a few different things. What's shown here is just measuring the linear slope of the light curves in units of the uncertainty, so just the sort of significance of that slope. That's a histogram for all the pixels in the HST image in black, and the best fit model is shown in red. The blue line is a model without any time variability, so just photon noise. And you can see that there's much more variation, much more variability than can be explained purely by photon noise. Over here, what's shown is the sensitivity of the model to the variation in age. And you can see that as you go to even somewhat younger ages, you get much larger fluctuations. And that's because the asymptotic giant branch is relatively much brighter at younger ages. It's also sensitive to the underlying model for these LPV stars. That we don't really understand how to model them in detail very well. And so we tried varying a few of the underlying parameters. In detail, we actually fit several different parameters quantitatively against these statistics. And the point is that the statistics of these light curves provide a strong constraint on both the stellar population age and on the underlying sort of physics of Mira variables. And the resulting best fit model is here, and the best fit age was 10 to the 10 years, which is consistent with what we think about that particular galaxy. What's more interesting, though, is thinking about the future. What's shown here is the flux contribution to these kinds of stars to the total integrated light as a function of age and waveband. And this is where our M87 data lands. It's kind of in the worst part of the parameter space. This is what we had to work with. So it's in a relatively blue band, not that blue, but relatively blue, and it's at old ages. And so what we're thinking about now is getting data in the near infrared for much younger ages, where you might expect of order 10% 5 to 10% fluctuations in the light. And so it's going to provide, we think, a new window into the ages of galaxies and into constraining these very evolved stars, which are very luminous and have all kinds of repercussions and implications for how we model galaxies. So this paper was published recently in Nature, and it got a fair bit of media attention. And like any press release, there's always a couple bad apples. And this was the worst offender. So there are at least two problems here. One is that, with all due respect to Peter Van Dockum, one of the collaborators, he was only one of 3 authors on the paper. The other 2 were here, myself and Jian Choi, a graduate student. And the second, of course, is that we did not discover M87. It's been known for at least 300 years. So anyways, this one gets an F for whatever. That's where I wanted to stop. Thanks.
John, in principle, it's a method for measuring redshift. If you can detect the effect of distant galaxies, you don't need to take a spectrum. You can just see the time being stretched.
Yeah, so we thought a lot about, if you had really high cadence over a long period of time and you took the Fourier transform of the light curves, you could actually see all the individual periods. There is a period luminosity relation, kind of like with Cepheids. So these are in some sense standard candles. You can imagine using these in that way as well. It is pretty demanding on the data, obviously, to provide that level of precision. But one thing we hope is that with some of the upcoming time domain surveys with a high level of precision, this will actually be an interesting, because the effect scales is the square root of n. And so as your pixel size increases, for say from the ground, the effect will go down as root n. But if you have high precision, you can still recover interesting things.
So in your pixel light curves, I saw things that are kind of rising or falling, but I didn't really see evidence in any particular pixel, like say a full sinusoid variation. So are there other things that may not be periodic that can contribute to the pixel light curve doing this thing? Say even just a small amount of gas moving along the line in front of one of these stars along the line of sight?
Yeah, it's an interesting question. We thought a lot about other things that could be going on, and I looked at about 5,000 of these light curves by eye. You actually see a lot of novae. We see potentially one microlensing event. And we thought about other kinds of stars. I think as you go to younger systems, and especially as you go into bluer or redder bands, you might see other kinds of variable stars on different timescales, which would be interesting. In terms of, one of the things is that there's not coherency on large scales in the signal, which suggests that it's really sort of a more local phenomenon. So we did a lot of different tests. I don't know about gas moving, in front of or behind the system. I suppose that could have some effect, but it'd be, I guess, surprising if it had the same overall statistics as the Mira effect.
And also the distance that anything moving in a few years is just 100 AU.
Yeah, about that. But if it's some cloud with some substructure and it's a 1% variation of blue band, I'm just not sure if that's out of the question. That could be that kind of variation.
Yeah, it's a good point. Part of it is, again, for the short baseline, you expect them to just be basically rising or falling. You don't expect to see a whole cycle over a 72-day window. So we want to try to get longer baselines as well.
Yeah, along the lines of James's question, but taking it a little further, there's a lot of variability that's stochastic and occurs over long time. For example, you might look at the galaxy at some point, and a number of mass transfer binaries are in high luminosity states. The next time you look, depending on the interval, they may be off and other ones may be on. You may not see a lot of variability, hour to hour, day to day, but over separate observations, there could be very significant variability. So I'm wondering, would you be sensitive to that type of thing, assuming you had the appropriate observations?
So one of the things we're excited about with future data would be to be probing a whole range of different variability, sort of that isn't thought of in this way so much as collective phenomena that can occur in host other populations. And I think one of the things that will help disentangle various variables is color information. So we only have one band, so it's difficult to rule out different types of variability. But with 2 bands or 3 bands, you can start to pull apart variability due to hotter stars versus cooler stars. So if the kinds of variability you're talking about are maybe hotter stars, and you would see it in the colors.
Any other questions?
How many novae did you see? There should have been a lot.
We saw 30 novae over 70 days, and they were all really faint. And if you try to put them on that relation of maximum brightness versus time scale, they sort of are a scatter plot across that time scale. But you're sensitive to pretty faint novae, which is it's separately kind of interesting.
Just to summarize, the blue that we have of the sky being frozen is just because we don't reach the precision 1% with our eyes.
That's right.
We can recognize the variation.
Yeah, so one of the press releases was Twinkle Twinkle Little Galaxy, which I also didn't like. But that's basically, in truth, the galaxies are flickering at the 0.1 to several percent level.
Let's thank Charlie again.
This certainly wasn't the audience that I expected. I sort of thought that there'd be 15 theorists and there's computation in the ITC, so 1/3 of them would be trying to figure out whether C code wouldn't lint, and another third would be asleep. And I was also told 10 minutes, so I made 7 slides, but let's see how it goes. What I wanted to do, I also thought it was supposed to be at least parenthetically related to the colloquium, and since I don't have a chance to talk about this at the colloquium, I thought I'd take the opportunity. And so when I first started out, it was 10 years ago, to propose an instrument for the GMT. Let me find these slides. Sorry about this. The most surprising thing happened, and I would go to these meetings where we discuss what instruments we want envisioned for the GMT, and people would say, "Oh, cosmology, how exciting!" And then other people would say, "Disks around T-Tauri stars," and people say, "Oh, that's so cool." You say, "But I want to find Earth 2.0," and the reaction was generally, "Why would you want to do that?" And the question comes up is, we're building, this will be the world's largest telescope in 2021 or 22 or 23 or something. Things have a way of sliding when you're building big things. And people say, well, why do you want to take up telescope time? And, the other thing, of course, we're doing is we are building, in fact, this instrument called GCLEF, which is a vacuum enclosed, thermally stabilized, better than 1 millikelvin per day spectrograph built out of space-age materials, composites. And people say, big apertures require big spectrographs. Big spectrographs are really expensive. We study bright things. Why would you bother taking this big aperture and pointing it at a bright star? There's going to be lots of spare aperture available in the ELT era when everybody thinks that an 8.4 meter telescope is tiny. And it's hard to achieve this level of stabilization. The HARPS, the Geneva group, is the only group that has really built an instrument that's highly, highly stabilized, that's operating today. Of course, the cosmologists, like I said, you're going to ask for dark time, which we will. It's going to be really great because we're going to be on the telescope first, and we have the bright time and the dark time. And then the biggest thing of all is they say, well, stars jitter. They have all these turbulating factors that make it very hard to do precision radial velocity. You'll never get there anyway, so why bother with this endeavor? So the first thing to say is you need a big telescope if you're going to find biomarkers. And I don't know whether, has Mercedes ever talked to you guys before? Mercedes did, I should turn this on, I suppose, if we're going to use it. Mercedes did and Florian Rodler wrote a really good paper analyzing what it takes to find O2 in the atmosphere of an exoplanet. And they really did they calculated, probability of rain, zenith distribution. They really, it's an incredible piece of work, and looked at what an instrument on the ELT or the GMT would look like. And the reason you're interested in O2 is it has this A band at 7600, which is accessible with visible band instruments. You don't have to go to the infrared. And actually, the technique has been demonstrated. It was pioneered by Ignaz Snell, and this is a Nature article 2007, data from CRIRES, where he detects CO in transmission in the atmosphere of HD 209458. And what you see here is this is the velocity, the detected velocity, and these are just spectra that are stacked up in time. And you see this sort of faint little scratch on here. And what he's done is he's taken the band heads of the molecules and all stacked them on top of each other to increase the signal to noise, but it's really there, okay? And so CO is, IR is harder, O2 is 7,600 angstroms is easier, but this is going to be a lot fainter. So the enabling trick here is, of course, you have this intrinsic line structure in your source, but you're looking from your ground-based facility up through the atmosphere with telluric absorption lines, and how do you tease them out? Well, it turns out because you have mutual line of sight velocity, and of course the planet's moving too, the Doppler shift moves these features out from under these features, and you can actually detect them. This is just a Barman model of M4V. So it's doable, and it's kind of out there. I hope it works, but I won't be surprised if we don't find it. But Mercedes and Florian did this very, very detailed analysis. And the bottom line you arrive at is that the sweet spot is probably M5. So G2 star realistically will probably take 37 years. You need about 37 transits, and if it's in the habitable zone, you only get one a year. And you have to factor in the fact that they've also factored in things like the fact that the transit might happen during the day, so you miss some. And so they think in about 37 years you would integrate up enough to see Earth 2.0 orbiting the sun. Stars that are later than M5 probably are kind of active. I suppose from a biologist perspective, they're sort of toxic environments to imagine life arising in. But they're also pretty hard to find, because you first of all find these things when they transit, and now you know the radius of the star, but then you really want to weigh that. I find the radius of the planet, but then you also want to weigh that planet, and to do that you have to do precision radial velocity measurements, and here the jitter of the star is really difficult. So multi-decadal observing programs are kind of hard to stomach. And I don't think you're going to do it well down here. So if I had to guess, I would guess that an M5 star is where we're going to find the first evidence of biomarkers. Now, the reason that you need a big aperture is that these, for actually almost any star, but especially for the middle of M, these things are really brief. You're going to need a lot of signal to noise to do this. You're not going to have a lot of time to collect the data. And so you need to integrate really, really fast and get to high signal to noise really fast. And so that's why. And read this paper if you want to. We need an ELT if we're going to find biomarkers around exoplanets. The other thing to remember is that although when you're doing in the context of precision radial velocity, when I say to most astronomers that I'm going to go off and observe a 14th magnitude star, you think you're doing that with the 1.2 meter, and this thing is so bright. But the truth of the matter is that when you're trying to measure the reflex motion of a star that's moving as fast as a Galapagos tortoise, 14 is probably undoable with any existing facility today, and might actually be undoable with an ELT. The good news is that George Ricker with Dave Latham has finally gotten the test satellite to the threshold of launch. It's going to do an all-sky survey for transiting exoplanets, or transiting exoplanet candidates. From Kepler, I think we This histogram illustrates our expectation of what sort of mass distributions of planets we'll find. And it's pretty well informed. I mean, that's not going to look exactly like that, but it will look something like that. And the important thing is that TESS is actually a fairly small telescope. Kepler was about a meter class Schmidt camera. These are really things you could clap onto your Canon single lens reflex camera. They're, I think, 150 millimeters in diameter, so they're really tiny. So this is a scatter plot of the transiting exoplanets detected with Kepler in blue and from the ground in green, and they're all pretty faint things. And there is no existing facility that will, and probably, as I say, even in ELT, that will get you down to the level where you can measure the reflex motion due to an Earth-sized planet around at least a G-type star at that level. So TESS, because it's tiny, but it's going to be all sky, we'll find zillions of thousands anyway, of really bright transiting exoplanets that hopefully we can find Earth analogs in. So the last slide here, though, is not my work at all. You may have heard about this before. Most of you have heard, because Ron and Dave talked to everybody. Dave Phillips is leading a team that's doing a funny exoplanet search to search for Venus. And they have a comb laser on the TNG telescope with the HARPS instrument, but the HARPS team doesn't want to give them the time to use their comb laser at night. Time's too precious. So one star that they will let them observe is the sun. And they did a rather elaborate calculation that showed that with this little 3-inch aperture telescope, I'm almost done here, 3-inch aperture telescope, you probably can detect the reflex motion of the sun in response to Venus in about 2 years. And so they're doing this now. And they get to look at the one star that's accessible to them. This is really cool stuff. I love it. But to me, the most important results came out in the first 5 minutes, or the first couple of hours when they turned this thing on. And this is just the raw data of 20-second exposures measuring the sun with this little tiny telescope at very high radial velocity precision. And you just see the 5-minute oscillations. So there are certain classes of stellar variability that this won't address, but if you can take really high cadence observations, so you have a giant telescope and you point it in an 8th magnitude star, and you're integrating for 20 seconds to get up to a signal of noise of 1,000, you're going to be able, you won't have to average over these observations to remove the effect of the stellar oscillations and jitter. You're going to measure them, and you're going to subtract them out. You're going to be done. And I think this is going to be transformational. I think it's why a whole new sector of exoplanet science is going to open up with the GMT. So I'll stop there.
Andy, of course, before these ELTs will become operational, there would be the James Webb Space Telescope, hopefully in 2018. And it doesn't look through the Earth atmosphere we're looking.
That's true.
So, will it not be able to detect any of these and get signatures of
It's not a very big telescope.
6.5 meters, but it doesn't have the atmosphere.
Mm-hmm.
So it will not be competitive in terms of detecting oxygen.
It doesn't. The thing I didn't say is you really need like resolution. You'd like resolution 2 or 300,000. This works at a resolution of 100,000. I'm unaware if the Webb supports that sort of spectral resolution. I don't think so.
So let's say if you find your target, you spend a decade observing it, and you detect signatures of oxygen too. Is it obvious that only a habitable planet will have that signal, or is it really a definitive signal? Or?
No. I mean, if you talk to Karen Oberg, who thinks about this stuff a lot, there are abiotic channels that would produce O2. You would need more, before you really could call it, stick a fork in it, it's done, you would probably want to have some other evidence that you probably want to have some infrared spectroscopy that backed it up.
Actually, there was a paper by Gene Kasky, collaborators, just a few months ago, arguing that even if you detect also methane, reducing
Mm-hmm. Mm-hmm.
But it would be would incentive people to take more steps, more data.
I mean, after 51 PEG was announced, I think it was 2 years when you were still hearing talks where people were saying, "Are you sure that's really an exoplanet?" And these things depends on how many of them you find and stuff. The really great thing is of course we're not observing it for 10 years. We're observing it for a couple of hours. It's just spread over.
The other piece of good news is that M dwarfs are not the smallest stars we know about.
Mm-hmm.
White dwarfs are much smaller, and they're the size of the Earth. And so the prospect for detecting, if we find transient planets around white dwarfs, that would be an excellent target because the occulting planet is of the same size as the source, the light source, and that is an area that was not studied. Observation is so far, whether there are planets in the habitable zone of white dwarfs.
Now, we always tend to forget that the first exoplanet was discovered around a neutron star. It gets lost in the wash sometimes, so that is interesting.
Other questions or comments? If not, let's thank
Right. Thank you. Thanks. What's that? Oh. I thought that was a gift to the speaker. Now I'm going to take it, Sam.
Is this from you? It's not yours. Okay. So we're going to switch gear and talk about cosmology and talk about neutrino masses, which are usually of interest of cosmologists and physicists, so bear with me. I'm Licia Verde, and this is my superposition of states. What I'm going to present today is based on this paper that was posted last week in the archive, and I should highlight the work of Antonio Cuesta and Viviana Niro, two young postdocs. Antonio Cuesta is actually visiting here, so if you have hard questions, I suggest you go and talk to him. All right, so since this is not the usual audience I talk about these things, let me introduce a little bit of background. What do we know and what we would like to know about neutrinos and their relation to cosmology? So from particle physics experiment, we know that there are 3 active neutrino species, sometimes called families, and neutrino oscillations, which you may have heard about because of the Nobel Prizes, indicate that neutrinos have mass, but can only yield mass differences. They cannot tell you what the absolute mass scale is. So given the mass differences, we know that there are 2 possibilities. It's either you have small split here and large split up there, or small, big split and small split. So this is called normal hierarchy. This is called inverted hierarchy. And of course, if the overall mass scale is much bigger than the mass splitting, you end up in what is called the degenerate regime. So this also means that the standard model for particle physics 1.0, as I call it, as it comes out of the box, needs some upgrading, because in that model, neutrinos are massless. So you need to come up with a mechanism that gives neutrinos their mass. So what we would like to know is, what is the absolute neutrino mass scale? And that is the total mass of the families, if we want to translate this question in a question accessible to cosmology. And ideally also, what are the individual masses, so we can know what the hierarchy is. And this has got some implication, again, for experiments in particle physics. So I will try to convince you that cosmology is the key in determining the absolute mass scale. So it is usual to show this plot. This is the mass of the lightest neutrinos, and this is the sum of the masses. These are the 3 sigma limit given by neutrino oscillation. This is the degenerate regime. This is the inverted hierarchy. This is the normal hierarchy. So the problem with cosmology, which I'm going to put my hand in front because of this, it's systematic error, because in cosmology we don't do direct measurement, we do an indirect measurement. But the other thing we want to take away from this plot is that there is a minimum mass for the neutrinos, given in this case by the normal hierarchy. And if you do the calculation, it turns out that neutrinos contribute at least to 0.5% of the total matter density of the universe. In the era of precision cosmology, this should be big enough to actually say it. So which neutrino are we talking about? We are talking about the cosmic neutrino background. When particle physics do experimenting neutrinos, they are higher energy neutrinos. They are not cosmological neutrinos. It's a relic of the Big Bang, similar to the CMB, except that it decoupled from matter after 2 seconds from the Big Bang, not 380,000 years. Let's keep on going. What are the physical effects in cosmology of neutrino masses? Neutrino with a total mass above 1 eV become non-relativistic before recombination, so one should see that in the primary cosmic microwave background, and indeed this has been done. Total mass below 1 eV become non-relativistic after recombination, so it alters the matter radiation equality, but the effect can be cancelled by degeneracy through other cosmological parameters if you only look at the cosmic microwave background. However, we have observation after recombination, and in this observation we see a different effect. We see that finite neutrino masses suppress the matter power spectrum on scales that are smaller than the free streaming length. And this is the effect one is talking about, is the ratio between the P of k divided by the P of k for 0 neutrino masses as a function of different sum of neutrino masses. And you see that in the epoch of precision cosmology, right, a 20% effect on the power spectrum should be able to see. And 20% effect is around 0.3 eV. There is also a higher order effect, which if I have time I'll come back later on, which is different masses become non-relativistic at slightly different time. And so in principle, cosmology can give information about the neutrino mass hierarchy, although that's much lower signal to noise. So this is the Katherine experiment, an ambition terrestrial experiment to try to measure the absolute neutrino mass scale. That's tritium decay, and that's the vessel. And the Katherine is working, but we don't have results. But the detection versus 90% limit will be somewhere there. The recent result by looking at Planck plus baryonic acoustic oscillation, 95% limit, put the limit there. So this is allowed, and this is ruled out at the 95% limit. But there's much more information than that in the sky, and that's what we want to use. There's no information about the shape of the power spectrum here. This is just information about early universe plus expansion history. If we want to go that, we want to use a larger scale structure, and again, we come back to this. So focusing on this, it will be of great value to have an internal consistency check. So if I have time, we'll talk about this later. So including larger scale structure clustering. Pros, you can see the signature scale dependent clustering suppression. Cons, there's astrophysical effect, which are poorly understood, at least in cosmology, and there is galaxy bias. So a possible approach, or at least a useful exercise, is to use completely different tracers of the dark matter distribution and see if there is agreement. And this is what we did in this paper here. First, the signature one is looking for. This is the same plot that you've seen before, but before it was in linear theory and no observational effects. And this is convolved with the survey, with the window, with the nonlinearity and all that. And this is the type of effect you see. And galaxy bias gets in the way, so all this line you want to, you can renormalize them up and down. So the effect is small. So the choice of the tracers, we choose luminous red galaxies, LRG, from the year 7, Sloan, from a paper that actually it's not new, it's 6 years old. And this has red luminous galaxies, and then blue emission light galaxies from the Wiggle-Z surveys. And this figure illustrates how these two different populations trace the dark matter in a different way. Blue galaxies avoid the high-density region. Red galaxies inhabit the high-density region. So they have completely different biases. If you find agreement between the two tracers, the bias is supposedly under control. And this is a figure of the actual observable. It's the galaxy power spectrum. This is the wiggle Z in the 4-redshift bin, and this is the LRG galaxies. We don't go beyond 0.2 because non-linearity gets important here, and we may try to model that, but there's uncertainty there, as well as Planck 2015 and baryon acoustic oscillation. So the methodology is the usual, the typical standard MCMC Boltzmann code, class plus Monty Python as out of the box, except for the luminous red galaxy treatment, because the likelihood was relatively old. They needed an overall due to the development for the aficionados on the halo fit, which were including the neutrino mass effect, which didn't have before. And for those that may worry about overfitting, this is an N-body simulation run independently from the one that were used to actually fit the halo fit. This simulation, we ran them in-house in Barcelona, and show that up to K of 0.2, which is where we are going to use it, there is good agreement, halo fit works. So here's the result, reproduced in a table and visually in a plot. What I want you to take away from this is that there's no detection, there is only upper limit. At the 95% confidence level, we have 0.11 when we use CMB, Planck plus LRG plus VAO, and 0.15 with the wiggle Z's. The effect you are looking for is something like this. That is, however, for illustration purposes only, because here is just the lambda CDM best fit model, and then only the neutrino mass was changed to be 0.2 eV, and all the other parameters kept fixed. But when you do this search, you vary all the parameters together. So the effect, the model with this neutrino mass will have other cosmological parameters that tend to adjust the error bar, the data better. So implication. LRGs are more powerful than wiggle Z, and if you just look at the sheer volume of the two surveys, wiggle Z is slightly bigger, so it shouldn't be that way. And this is due to the survey window. For the aficionado, this is a picture of the survey window. For the non-aficionado, let me just explain. Wiggle Z is composed of several different pencil beam-like areas, while SDSS looks at the entire volume in one chunk. So implication number one, since I have another half a minute. This is excluded, this is allowed, not the bracket given by the oscillation, so that's here. Implication number two, for tritium beta decay, cosmology puts the cut here, and this is the sensitivity area, so the inverted hierarchy, there's only a little corner left. For the pessimist, the inverted hierarchy is under pressure. For the optimist, if inverted hierarchy, then a measurement of neutrino mass is just around the corner. For those of you who are interested in neutrino less double beta decay, to see something, you need at least a ton scale experiment. This is the sensitivity area of neutrino less double beta decay, depending on the hierarchy, normal or inverted. Now, this is what is called the nightmare scenario, because for the normal hierarchy, there's a regime in the sum of the masses and the effective mass where they're not sensitive at all. So go down there. Imagine we measure a non-zero neutrino mass. How do we know that it looks like a duck and it quacks like a duck, and we haven't seen something else? So one possibility, and I really conclude, is that the hierarchy has also got some effect on the shape of the linear matter power spectrum, because neutrino of different masses have different transition redshift from relativistic to non-relativistic behavior, and their individual masses and mass splitting changes the detail of the radiation domination to matter domination. So this is the response of the power spectrum to this mass splitting. So it is the parameterization. If the parameterization you choose is something like that, then you can write everything in terms of this big delta. So it turns out that cosmology is mostly sensitive to the absolute value of this delta, not the sign. However, this still offers a powerful consistency check, because if you say that the neutrino mass is, whatever value, you should know what oscillation tell you this absolute value of delta should be. And then you should go and measure it. If you find that the absolute value of delta is something else, it's likely that what you've seen is not neutrino mass, it's some other effect that act like it. What it will take to instead measure not just the absolute value, but the value of this splitting, the ultimate experiment, but in combination with neutrino-less double beta decay can help answering the question, are neutrino Dirac or Majorana, are they an antiparticle or not? So let me come up with conclusion because my time is up. Cosmic neutrinos are out there, but now it's a question. So we have the precision, like the scale structure data, I have the potential to measure the neutrino mass. But precision is not enough. We have to move towards accuracy. And robustness, use different tracer, red galaxy, blue galaxy. Also, there was recently a measurement done by, again, the Sloan collaboration using the intergalactic medium, the Lyman alpha. And from the Lyman alpha, which is traced the intergalactic medium, they found a constraint of the neutrino mass that is totally consistent with what we find using galaxies. Which, again, offers some more support to the fact that you're using completely different tracer yet get the same answer, cross-checking the modeling and consistency check. Now, LRG result use a P of K from 2009, 1 gigaparsec cube volume. That's DR7. DR12 have almost an order of magnitude bigger volume. So we could soon be surprised. And I'll stop here. Thank you. Okay. So there is one key step that must be done. So in order for DR7 to come out with that nice power spectrum, a previous operation was done on the actual galaxy distribution. So it was calibrated that it's true the red galaxies live in halos, but how many are one galaxy per halo and how many do we have two galaxies per halo? So this was calibrated and the halo field was estimated from that. And then the subsequent analysis is much, so you get something that is closer to the theoretical prediction because you use more information than just the power spectrum, you use the full phase information. Now, to do that on DR12 require having simulations that have the halos that until a year and a half ago we didn't have because you need enough volume and enough resolution to do that. So now I think now we're getting there and probably somebody is already doing it. I don't know if it's in this building. I need to find out because that's one other thing that it will be natural to do next, but it makes no sense to duplicate effort. Also, for a claim like this, you want to use data that have been out for a few years, that people have tried inside out, they're criticized, and you know that works. You want to do it one step at a time. And in case we want to do it for DR12, I would suggest to first present the power spectrum, let the community to, try it out and shake it as much as possible, and then go and do this kind of measurement. Good, thanks.
Okay, time for Le Lanterne Rouge. So thanks again for having me here, and I did a very good job. I tried to make sure that pretty much everything I had in this talk was not talked about at all in the last one. So my collaborators are completely different because I'm going back to some of the work I did for my thesis at Berkeley. So basically, we talked about a little bit in my last talk. Galaxies form a pretty nice bimodality, and it turns out the bimodality sort of selects a particular kind of galaxy. So red sequence galaxies are galaxies that are red in color, and early type galaxies are galaxies that lack spiral structure. And I am very proud of this plot because it meant that I got a Venn diagram into my thesis and it was scientifically relevant. So over on this side, this is not the side I'm going to talk about, but it's really fun to study outliers because, again, early type galaxies are galaxies that have transitioned. So potentially you can learn a lot about galaxies that sort of don't fall inside of this transitioned, quiescent, red and dead category. But I'm going to leave the work to Ren Binyan, Karen Masters, and Kevin Bundy to give you a great idea of how red spirals work. And I'm going to actually focus over here on blue early type galaxies. So the way that we came about doing this was actually through the Atlas 3D survey. That is a volume-limited survey of 261 nearby early type galaxies. When Michele Capillari set out to do this, it was using the Sorin instrument, which was one of the first infrared field spectrographs on the William Herschel telescope. And what he picked things that were within 42 megaparsecs, so you could see them. They needed to be massive. They needed to be visible in the north. You really didn't want them on the galactic plane. And of the 871 possible galaxies, Michele looked at all of them by eye to look for spiral structure, and he found 261 of them were early type galaxies. And when you look at them on the color mass diagram, they lie here. So the green spirally things are spirals, and the red and the blue are Atlas 3D galaxies. The red blob actually stands for slow rotators, that is dispersion-dominated early type galaxies, and the oval and blue one is actually fast rotators, which are rotation-dominated early type galaxies. But what became very interesting about this, not only did we have an unbiased sample, is we actually pointed molecular gas searching telescopes, that is the EROM 30 meter, at all 261 of these galaxies. And what Lisa Young found was that 22% of early type galaxies contain a molecular gas reservoir. So before this, people had found weird ones. You could find things that were far infrared bright that were early types. But this told us that a significant fraction of galaxies we considered red and dead were not indeed red and dead. And so we looked a lot for where these galaxies laid, and as you might expect, blue early type galaxies tend to have molecular gas. There was a strong preference for rotation-dominated objects, and what that means is it turns out in galaxies that are what one might consider true ellipticals, M87-like objects, truly dispersion-dominated, slow-rotating galaxies do not seem to have reservoirs of molecular gas, but the rotation-dominated objects, that is, ones we might consider S0s or lenticulars, do. And again, Green Valley objects are more likely to contain molecular gas. But as you can see, there are still plenty of galaxies that are truly on the red sequence that have molecular gas. So what did we want to do next? Well, this is where I came in and why I love karma. So what we did was we actually mapped a ton of these early type galaxies. So what I have here is I have the list of the CO-detected Atlas 3D galaxies. The galaxies that are shaded in light blue are galaxies that already had molecular gas maps. Before this karma survey, there were only about 20 CO-imaged early type galaxies, split sort of between some work from Joan Roble, Jeff Kenny, Lisa Young did a lot of it, Francois Combs, Lisa Way. But here's what we did when we did the karma survey. We mapped another 30 of them. So now there are 50 early type galaxies that have molecular gas maps. And here's the sample of some of those. I point this out just sort of to show you, again, karma creates beautiful, beautiful images. There are a lot of different structures, a lot of places where the gas is regularly rotating, nothing interesting, and some cases where you have things like minor mergers. And I wanted to point out, every single one of these CO maps is public. You can get it either by emailing me or going to pearl.org/atlas3d, which has all of the data from the Atlas 3D survey public and available for people to download. We made sure that these data were survey quality, which means lots and lots of work, but we did it well. So you should be able to grab these data if you want a sample of CO in early type galaxies. So some of the major results that came out, again, this is Atlas 3D. We have We have a lot of data. We have great data on this, including the stellar kinematics and the gas kinematics. So something Tim Davis did that was really interesting was he actually took the gas kinematics and compared it to the stellar kinematics. And what you can see here is that overall, gas and stars are aligned pretty much all the time in Virgo, and only about 50% of the time in the field. In the field, there are a lot more cases where the gas is misaligned from the stars. And this meant a couple of things. This could mean that inside of Virgo, you're in a situation where you can no longer create external gas. So this was either gas that the galaxies came into Virgo with in situ, or potentially this is gas that was acquired and condensed from stellar mass loss. But we went a little bit further than this. Lucky for me, maybe actually unlucky because the data reduction was a bit of a pain, CARMA was able to simultaneously look at 2 different isotopal logs of CO. We were aiming for 12 CO to get our images, but we came with a freebie of 13 CO, which is actually tracing, again, 13 carbon is much less abundant than 12 carbon, so you're tracing something that is much more optically thin. And what we found was sort of serendipitously, we detected 13 CO in a lot of these galaxies. In fact, in 6 of the 18 that we have 13 CO observations, we actually had enough signal to noise, again from 12 CO observations, to detect and image the galaxies. But what we then did was we used work that was done by Andreas Schruba to stack the spectra to see if we could detect 13 CO and more objects. When I say stacking, what I mean is I actually use an a priori mask saying if there's 12 CO in a place, that's probably the place I should look for the 13 CO, and use that to basically create a channel map. And all of a sudden, what we did is we went from having 6 out of 18 objects that we really detected well to 15 out of 18 objects. So we now have a really great sample of 13 CO to go along with that 12 CO. But the thing that became interesting, yet again, was when we looked at Virgo. What I have here is I have all of the 13 and 12 CO measurements that I could find in the literature for not only early type galaxies, but also for late type galaxies. And what you can see is overall, for the most part, things peak sort of at, 0.07, probably, 13 CO to 12 CO luminosity ratio. I guess it's actually a flux ratio in this case, excuse me. But you can see that the distribution of spirals and the distribution of mergers tend to be sort of at the low end. But then you get into early type galaxies and you see that this distribution starts to get much larger. So we're trying to figure out what that was. Well, turns out galaxies that have early type galaxies that have disrupted molecular gas have low 13 to 12 CO ratios, which supported the work that was done by Suzanne Alto in about 1995, saying basically that by clobbering these things together, the optical depth of things is changing in such a way that your 12 CO is enhanced and your 13 CO is not. Field early types, though, also tended to have things very similar to these spirals. So it turns out that the reason that this early type galaxy distribution is seen is almost solely because Virgo tends to have very large 13 to 12 CO ratios. That Virgo overall has something between 0.1 and 0.3 and has some of the largest 13 to 12 CO ratios that we've seen. So that we found extremely weird. Now, even though this is a slide that is my end, I'm going to put forward 3 hypotheses to you, and debates can happen, and in fact, potentially more hypotheses can come out of this time that I'm here. So the first hypothesis is that this is a stellar reprocessing event. So the good news is we now know Virgo, the gas in Virgo is not coming from an external source. You're not getting primordial gas. That means that if stellar processing, as galaxies, as the more massive older stars are putting out new gas into your system, if that gas is 13 carbon rich, you're in a situation where you might actually see this enhanced ratio because of enhanced abundances in those galaxies. Virgo's not getting new gas, it's not getting primordial gas, maybe that's it. The second possibility is mid-plane pressure. That is, in Virgo, you have a lot more pressure that is actually condensing your molecular gas disks, and that is what's creating the high optical depth. The third, which is actually my favorite, is the one I like to call survival of the densest. That is, if you look inside of the galaxy, you find that these are the same. Doesn't matter. You find that the 13CO to 12CO ratios in the biggest, densest, bulkiest giant molecular clouds in the Milky Way are actually up here. So potentially, this is actually a ram pressure stripping incident where the ram pressure stripping is not just affecting the neutral gas, it's also affecting the molecular gas. That is, giant molecular clouds that are smaller, that have lower ratios, are actually being preferentially evaporated out of Virgo galaxies as those galaxies are interacting with the intergalactic medium. And again, those are my 3 hypotheses, and I am done with my talk.
Can you measure some molecule associated with nitrogen? Because instead of constant thing, we would also expect to see the N ratio to be different.
We can do molecular gas, we can do CN. We haven't done CN for these. It's at 113 gigahertz, but that's definitely one that, yes, we could absolutely do. My worry about it is in NGC 1266, which is this AGN-driven molecular outflow, the CN is the only molecule that looks completely different in terms of its kinematics and what its structure is, and looks like it's actually tracing the outflow in some really odd ways. So I'd be worried that CN, we might actually have some contaminants in it. But CN would actually be a molecule we could test.
So if you go a little deeper, maybe with ALMA, and you're able to do 13CO versus a C18 level, that would show you whether it's a noticity effect or an optical depth effect.
Yeah, one thing I'd really like to do for these is actually image the individual giant molecular clouds. Again, these things are in Virgo. This is a pretty nearby cluster. And we know from some work that Diasutomo did, looking just at the 12CO with the really expanded karma, which had 0.1 arcsecond resolution, is he was actually able to individually pick out giant molecular clouds and giant molecular associations, and I believe NGC 4526, which means with ALMA, you should be able to do this almost trivially. Because again, you're looking at 1/3. You're really not looking for much extra time to get the 13 and 12 to see if the structure and the distribution of GMCs is different as well. But yeah, C18O, dense gas, the reason we actually could rule out fractionation is because Alison Crocker has worked, she's done on the dense gas in some of these systems, only maybe 10 of them. And the dense gas actually showed that the ratios were not so different that that this was a fractionation effect.
It looks like in all the 4 presentations we heard today, there is a common thing. More data would be very
Always.
Thank you very much.
Thanks.